Okay, 3D, reciprocals of other functions. So what we're doing is we're starting with some function, and then we're going to graph the reciprocal of 1 on top of f of x. So you should remember, like from lines, when we're doing equations of lines, we have a perpendicular line as the negative reciprocal of slope. Good. So we've got, this is a quadratic, okay, we've got the 2 roots. And so from this, like I would expect you guys to be able to look at that and to produce this graph, right? Okay, the root is -2, the root is +1, all right? Has a positive a value, which means it's opening upwards. The axis of symmetry occurs exactly halfway between these roots, okay? So that axis of symmetry, halfway between them, so that gives us an x value of -0.5, and then we can find the y value by subbing that in here, okay? So I expect you to be able to produce that, no worries. We can use our calculator to help us as well. So let's look at the properties that a reciprocal function is going to have. The zeros of y equals f of x are going to become vertical asymptotes of 1 on f of x. So let's explain why that's true. So if this is f of x, and then our new function then is going to be y equals 1 on top of x take 1 times x plus 2. So here the zeros are +1 and -2. And the claim is they become vertical asymptotes. Well, of course that's the case because when x is 1, the denominator is 0, we have undefined, we have the vertical asymptote. When x is -2, the denominator is undefined, and we have a vertical asymptote. So on our new function then, on our reciprocal function, we're going to have vertical asymptotes at x is 1 and x is -2. They're going to be vertical lines at x is 1 and x is -2. Good. Okay, then we have vertical asymptotes on this function are going to become zeros. They're going to become the roots of y equals 1 on f of x. Now this function does not have any asymptotes. Quadratic doesn't, so we can ignore that dot point for now. Local max on f of x become local minimum. All right, we don't have a local max, but we do have a local minimum, which means the 4th dot point is going to be pertain to us. The local minimum here is going to become a local max on y equals 1 on f of x. So if we're talking about properties of 1 on f of x, all right, let's start listing them. We have vertical asymptotes, and we have a local max at, and the x value is going to be -0.5.
But the y will become, like the sign will change.
Excellent. The y is going to become 1 on top of, we could put 0.5 in here, but we already know from our graph that when you put 0.5 in, this value becomes 9 on 4. So the y value, let's make the argument here, is going to be 1 on top of, well, -9 on 4. All right. Now, when I'm dividing fractions, I like to think about it in terms of 2 fractions, as a on b on top of c on d. Now, our division is there. That's where it corresponds. It's 1 divided by c on d. So that means we're going to write this as 1 on top of 1. And AD on BC. All that's happening is that they're flipping. All right, we're forming the reciprocal of it. Whenever you have 1 divided by something, it reciprocals it. So the y value of the local max is -4 on top of 9. Okay, and then what else do we have? When f of x is positive, 1 on f of x is positive, that makes sense. 1 divided by a positive number is positive. And when f of x is negative, 1 on f of x is also negative. Okay, 1 divided by a negative number is also negative. Okay, and then the last dot point. When f of x is approaching 0, 1 on f of x will approach positive or negative infinity. And when f of x approaches positive or negative infinity, 1 on f of x will approach 0. So with this quadratic, we know that at its extremities, as x approaches positive infinity, the y value is just going up forever as well. The y value is approaching positive infinity. So that means 1 on f of x, okay, when we have the 1 on f of x function, as x is approaching positive infinity, well, we have 1 divided by positive infinity, it's going to be approaching 0. I'll make the argument for you now, but we can know that just from reading. Okay, so what we're asked to do, find the reciprocal function and state its domain and range. Okay, so firstly, here's the reciprocal function. Okay, so that's our answer to part A. The domain that we have is that x does not equal 1 and minus 2. That's the first part. And the range is going to be a little bit more tricky. Let's start to make an argument around what's happening as we go out and at the local max, what's occurring there. So if I'm going to start producing a graph of this function, right, what I know is that it has asymptotes at x is 1 and asymptotes at x is minus 2. Asymptote there. I know as well that there's a local max at this point here. X is minus 0.5. So I've said that's minus 2, that's minus 1. So that's going to be minus 0.5. And then the y value minus 4 and 9. I haven't defined a y axis, so there's going to be some local max there. All right, so we can anticipate what's going on here is it's going like this. Okay, it's not going to have any roots either side of that because asymptotes on f of x become roots. So this function is not going to have any roots. All right, we know that as well because roots would occur when this function equals 0. And for a rational function, it will equal 0 when the numerator is 0 and 1 does not equal 0. So it's not going to have any roots. We've got those asymptotes clearly defined. We've got this local maximum part. So now we need to define, and I'll list the coordinates there, minus 0.5 and minus 4 or 9. Now we need to define what's going on out here and out here. And so all we're going to talk about is what happens as x approaches positive infinity. Okay? As x gets really large in that direction, what's going to happen to this function? We're going to have infinity multiplied by infinity. We're just going to have a really large number. This is how I should make the argument, by the way. As x approaches infinity, y approaches 1 on top of infinity. All right? Which is 0. 1 divided, okay, 1 cake divided by infinity amount of people, it approaches 0, but from the positive direction. Okay, now what I'm applying there really is the last dot point. So the last dot point and the second part of it. When f of x approaches positive infinity, 1 on f of x approaches 0. Of course that's true. When this function, as x increases, the y value is approaching infinity. And so 1 divided by infinity is going to be approaching 0, and from the positive direction, because this component, despite approaching 0, it's still positive. There's no negative involved in that calculation. So what that means, we have a vertical asymptote here, and it's approaching 0 from the positive direction as x gets large. This is what it's going to look like. Okay, and make this argument as it approaches negative infinity. Okay, what we'll have at the bottom, we'll have negative infinity multiplied by negative infinity. You don't have to think about infinity, you can just use 1,000 or even 100 or any number really, like you're just putting in a big negative number. A big negative number multiplied by a big negative number. The result is positive. Okay, so we have 1 divided by a big positive number. It's approaching 1 on top of positive infinity. And so it also is approaching 0, but from the positive direction. And so that's what's going to be going on here. Okay, we have approaching 0 from the positive direction. Approaching 0 from the positive direction, that's our x-axis. And then being asymptotes here and not having a root, we know it has to go in that direction. Okay, so let's answer the domain and range then. We've got the domain. As for the range, so what you can see for the domain is that it exists for all x values except here and here. For the range, all right, we can see that it exists for values greater than 0. Y, remember when for range, we're talking about possible values of y. It exists for values greater than 0. And values less than or equal to minus 4 or 9. Okay, why do I use greater than here and not greater than or equal?
Because it can't equal.
Very good. It can't equal, it's asymptotic at 0, and I include that point because that's the local maximum. All right, so range, those values, and those values. It doesn't exist in this region. Cool. Excellent. Now let's just show you guys quickly on the calculator. The only thing I want to point out, like you're pretty familiar with, I might make it a little bit larger as well. Calc, let's just go normal. Screen, normal. I'll just move it so I've got some space so you can see. Yeah, the only thing I want to point out is, let's say we've got the function there, x take 1 times x plus 2, and notice how it says y1 equals. So then what I'm going to do, I come down here, and you don't actually have to type out the whole thing again. Instead, you can go 1 divided by, and then look at all these buttons popping up here, y, r, x. So we're going to press F1. F1 corresponds with y, it's in the first position. And so I'm just going to go 1 divided by y1. It just saves you time in typing the whole thing out, especially when you've got really long functions, which you do tend to deal with a bit as well. The other thing is I've only got the red function selected. Okay, so we know how to select functions using F1 as well. All right, I'll come around and see how you guys go with that. But we can select the red function, and it's only going to graph the red function. And we can see it's got the same as what we've got. Calculator's having a freak out at those asymptotes, but we know that that's where they exist. Really good. All right, so this exercise is pretty straightforward. Where it will get tricky is when they give you a graph and they say find the reciprocal function from a graph. So when we get to those, maybe we can have a wrestle with them together. But for now, let's dedicate our efforts here.